Okay, so moments. So a moment is the turning effect that you get when you apply a force to something that is able to turn, something like a pivot or a lever. So the actual definition of a moment is the turning effect caused by a force. And there's lots of common examples. So, like I say, turning a door handle, using a spanner on a nut, seesaw in a playground, that kind of thing. But what you need to be able to do is calculate the moment of a force, so the turning effect of a force. So to do that, you need to know two things. Number one, you need to know how big the force is, the size of the force. So, obviously a bigger force is going to cause a bigger turning effect. And then, taking into account the fact that force is a vector, so the direction of that will matter, that will then help you determine something called the perpendicular distance from, so we don't say just from the force, but we say from the line of action of the force. And we'll look at that in just a moment. So the perpendicular distance from the line of action of the force to the pivot, or the pivot point. So obviously with that, we need to have a look at what those two things actually are in a real life situation, so we can see where we would get those measurements from. So let's take a very simple lever. Let's take, for example, an everyday sort of lever door handle. So I'll attempt to draw something that vaguely looks a bit like a door handle. Okay, so here's our door handle. This is the edge of the door. This is the bit we're going to push down on to turn it. So here's where we would put the force. If we push down on the handle here, that's where the force is being applied. The dotted line is the line of action of the force. So you just carry the line on in the direction the force is being applied. That's the line of action of the force. So that sometimes becomes really important. In a lot of situations, actually, you can just deal with the force where it is. The handle moves down like this. This is the point that, in effect, seems to stay still. It rotates around that. So we call that the pivot point. You may see it in all books labelled as the fulcrum. So we have the force, the line of action of the force, and the pivot point. If we then, in this case, go along the actual handle to where the line of action of the force is, you'll notice these are perpendicular 90 degrees to each other. So that green line there, the distance from the pivot along to that line of action of the force, as long as it's at 90 degrees to it, that then is the perpendicular, because it's 90 degrees to, distance from the force, or the line of action of the force, to the pivot. So what we've got there then is the force, line of action of the force, pivot, and then from that line of action of the force, you find 90 degrees from there, straight to the pivot, which in this case is straight along the lever. That's the perpendicular distance to the pivot. Most situations you will have to deal with, the perpendicular distance to the pivot will be along the thing that you're actually dealing with. So if it's a seesaw, for example, it'll be along the beam of the seesaw. If it's a spanner, it'll be along the handle of the spanner. We will look at what happens when it's not quite like that, but that's something we can sort out in a moment. So let's take the same idea. Let's have a beam. Let's stick the pivot at the end. But this time, let's have the force applied at a bit of an angle. So this time, the line of action of the force, carry that on in a straight line in both directions. And now what we're looking for is somewhere where we come off that at 90 degrees to it. So it could be here, that's 90 degrees to it. It could be here, that's 90 degrees to it. But we need a line at 90 degrees to it that actually goes to the pivot. So obviously, they're not going to go for the pivot, so they're no good. So in effect, you go along with a right angle triangle, find 90 degrees, it points then to this line here. So in this case, that is the perpendicular distance to the pivot. We'll call that D for perpendicular distance to the pivot. So again, you've got the force, let's label that F. You've got the line of action of the force, which is a line carrying on forever straight through the force arrow, so you can see which way it is in effect having its effect of the force. And then this is the lever we're pushing on. Here's the pivot, so we need to find somewhere that comes off this line at 90 degrees to it but goes to the pivot. And there'll only be one place, and that is the perpendicular distance to the pivot. You will get very few, if any, situations where you have to deal with a force that's not already just at 90 degrees to the pivot, like it is in the door handle, in which case then you can just measure along the lever to get the perpendicular distance. So to use those to work out the moment is going to be equal to the size of the force you're applying multiplied by the perpendicular distance to the pivot, which means force is measured in newtons, perpendicular distance is measured in meters, which means a moment is measured in Newton meters. Now, as you know, from work done equals force times distance, work done is joules. Joules are also Newton meters. However, when it comes to moments, we always leave it as Newton meters. We don't change it into joules. So the turning effect, the moment, the turning effect of a force, whilst technically it is the same as joules, we always leave it as Newton meters. It helps distinguish the fact that that's a turning effect and not just an amount of work done. So let's just do a couple of quick examples. So let's take one which is simpler and more straightforward. So let's say you have some kind of lever. You have the pivot at one end. Now the force, it can be hanging off the bottom of here or pushing down. Let's go 20 newtons, and let's say that perpendicular distance is 2 meters. So the moment equals the force times the perpendicular distance to the pivot. So we've got 20 newtons multiplied by 2 meters. That gives us, of course, 40 Newton meters. But force is a vector, has a size and a direction. Moments are also vectors, so we have to have a direction with the turning effect. So as we are looking at this, this is 40 Newton meters, and it would be having an effect to turn it this way, which is clockwise. So we would have here clockwise, and we should technically say about the pivot. And if there was more than one pivot, we would identify which pivot it meant. So you could have two pivots, that'd be A and B. So you'd work out the moment about one of them. You say clockwise about pivot A, for example. So that's the kind of the simplest version of the lever. Then let's take one that's slightly more complicated. So let's take a seesaw of some description, and let's stick two forces on here. Let's stick one force on this end, 20 newtons, and let's have a different force on this end, that's 10 newtons. So here we've got the 10 newtons is trying to turn the thing this way, the 20 newtons is trying to turn the thing this way. So each one of these forces has its own turning effect. So what we have to do here is look at the turning effect of one, look at the turning effect of the other, and then see what that means overall. So if we go, let's deal with the 20 newtons first. So the moment of the 20 newton force helps if we have some distances. Let's have 2 meters there, and let's have the pivot in the center, so 2 meters there. So the 20 newton force is going to be 20 newtons by 2 meters, so it's going to be 40 Newton meters, and this force is trying to turn, if you imagine the levers there and your pivots there, that's going to turn it clockwise. If you struggle with this, get a small ruler, put your finger where the pivot is, and use your other hand to push down where the force is and see which way the ruler wants to turn. That's a good way of kind of helping get your head around the situation. So that's 40 Newton meters clockwise. Shorthand, you can get away with just putting a little C and an arrow to show clockwise. But then we also have the 10 Newton force is 10 newtons by 2 meters, which is 20 Newton meters, but this one is turning it this way, so that's anti-clockwise. And then, as far as this beam's concerned, it's got this 40 Newton meter clockwise turning effect, but also got a 20 Newton meter anti-clockwise turning effect working against it. So if we were to combine those, then we would have an overall effect, or a resultant effect, would be, we've got 40 Newton meters clockwise, take off the 20 Newton meters anti-clockwise, so that leaves us a total of 20 Newton meters clockwise. In other words, this 20 newtons is having a 40 Newton meter clockwise turning effect, but this 10 newtons here is having a 20 Newton meter anti-clockwise. So obviously overall 20 Newton meters anti-clockwise, 40 Newton meters clockwise. The overall effect is just 20 Newton meters clockwise. So situations where you've got more than one turning effect, you have to work them out individually, decide whether they are clockwise or anti-clockwise, and then combine all of those together to work out the overall effect. You can't just quickly combine them. Let's do another example that sort of looks at a similar situation to that. So let's have the pivots over here this time. Let's have a 5 Newton and a 10 Newton. Let's put some distances in. So this one can be 3 meters from the pivot. That one can be 1 meter from the pivot. In questions, watch out, quite often they'll give you distances between the forces, and then you'll have to add them together to work out the whole distance across the lever. So it's annoying, but it's just something they do sometimes. So again, deal with them one at a time. So my 5 Newton force is 3 meters away from the pivot. So that's going to have a turning effect of 15 Newton meters, and this is going to turn it anti-clockwise. I've got a 10 Newton force that is only 1 meter away from the pivot, so that's going to have a 10 Newton meter turning effect, but again, this is also going to turn it anti-clockwise. So what I've got now is I've got one 15 Newton meter anti-clockwise effect and another 10 Newton meter anti-clockwise effect, so they're helping each other. So in effect I'm going to add those together because they're helping each other. So those two combined give me a total of 25 Newton meters anti-clockwise. Notice there is no way of combining the 10 and the 15 with either of those distances to get that. So you have to deal with each force and its turning effect separately from any other force and its turning effect. You can't combine the forces. The only time you could if they were both acting on exactly the same point of the pivot, and then you could resolve the forces first and then just use the resultant force to get its turning effect. So a common use of taking advantage of moments is to use them as levers, sometimes called force multipliers, which is a little bit misleading, but what these do is they allow you to apply the same force that you can apply, so there's a limit as to how much force you can apply, but by using the pivot effect and the lever effect, you can actually lift something heavier than you normally would. So a good example of this, for example, is a wheelbarrow. Okay, so the wheelbarrow, you have the wheel on the ground, you have the handles where you lift, and then you have the load in between the two. So what you've got here is pivot point is the wheel. You've got the load here, which is what you're trying to lift, and then you've got the force, sometimes called the effort. That's what the force you put in here, which is counteracting it. So what you've got is the load is trying to have a clockwise effect about the pivot, and you're putting in the effort to have an anti-clockwise effect. So what this means is you can use this to lift something here that you could not normally lift. So let's say we've got a load of 200 newtons and your maximum effort that you can put in is just 50 newtons. So if you just had the load if it's 200 newtons of weight, then with your best 50 Newton lift, you simply can't lift that. There's always going to be a greater force down. It's always going to accelerate downwards. You can never raise it. So this 50 newtons cannot lift the 200 Newton load except by taking advantage of the lever principle. So let's put some distances in along here. So if we remember that we're dealing with the lines of action here, so I'm just going to extend all of these to make life just a bit simpler. So you don't measure along the wheelbarrow to the handle, because that's not where the lines of action are happening. The lines of action are happening here. So your distances are in a straight line perpendicular from here, from the pivot point, to the line of action of each of those forces. So you've got this one here, that's quite close. Let's call that 0.2 meters. And then we've got one here, which I'm not going to say what it is yet, but we'll see what that is. So you've got line of action of the force for the load, and here's its perpendicular distance to the pivot. Line of action of the force of the effort, and here is its perpendicular distance to the pivot. Strictly speaking, I should probably draw that here, but then obviously it overlaps with this one. But if I take the line of action of the pivot as well, it's very obvious that this distance here is exactly the same as that distance there, so I can just move that up a bit to make it easier to see. So the question here would probably be along the lines of how great does this distance need to be in order for this 50 Newton effort to be able to lift that 200 Newton load? So what can we do? What can we work out? Well, here we know the force of the load and the perpendicular distance to the pivot, so we can work out the turning effect the load is having in the wheelbarrow. So here we've got 200 newtons, that's the force, multiplied by 0.2 meters away from the pivot. So that gives us a turning effect of 40 Newton meters, and that is having a clockwise effect. So in order to lift that, we need to have our anti-clockwise effect of the effort here and its perpendicular distance to equal that, to in effect lift it. Once it's lifted, keep it balanced, and then slightly more than that in order to lift it and change it in the first place. So what we need to do is make that equal to the same. So we can go over here. So we know that we need this 50 Newton effort multiplied by how far away it is from the pivot. We know that needs to equal 40. So we can look at that. We go, so we know it needs to equal 40, so we need 50 times something to equal 40. Rearrange that's probably the easiest way. 40 Newton meters divided by 50 newtons is going to equal the distance we need. So we need a perpendicular distance to the pivot of 0.8 meters in order to divide that 40 Newton meters in an anti-clockwise direction in order to counteract the 40 Newton meters I've got in a clockwise direction because of the load. So this is why it's sometimes called a force multiplier, which is a slightly misleading name. You've got a smaller force, but by applying that force a greater distance away, we can get the same turning effect as the much larger 200 Newton force that's much closer to the pivot. There is a trade-off. I mean, the trade-off is in that in order to lift this load a small height here, we would have to lift the handles a much bigger height here. So that's the trade-off in terms of the physics. You're not getting anything out of it for nothing. So yes, you can put in a smaller force and get the same turning effect, but the trade-off is you have to lift the thing further to get a smaller height gain here. So there's no sort of way of creating or making energy out of nothing. You're still doing the same amount of work, but you're just changing it so that you're doing an increased movement, but with a smaller force, in order to get a bigger force to have a smaller movement. So it all trades out. So that's how levers work. So in there, we introduced the idea of things being balanced. So I'm just going to make a statement here. So we're going to say, when in equilibrium. So what that means is when something's in equilibrium, it means all the forces are balanced. In other words, there's a zero resultant force, nothing is changing. So when in equilibrium, obviously all the forces are balanced, but at the same time, the sum of the anti-clockwise moments, that's a nice way of saying all the different forces that are trying to turn it anti-clockwise, add up all their turning effects. So don't add the forces, work out the turning effect of each one, add them all together to find the total anti-clockwise moments. So when in equilibrium, the sum of the anti-clockwise moments, so all the anti-clockwise moments put together, that's got to be equal to, in other words, cancelled out by the sum of the clockwise moments. So that's quite a long-winded way of saying if the thing's in equilibrium, in other words, nothing's changing, then the sum of the anti-clockwise moments, so all the different forces and their anti-clockwise effects taken into account, is equal to the sum of the clockwise moments, so all the clockwise forces and their turning effects in a clockwise direction are cancelling out all of the things trying to make something turn anti-clockwise. So let's do an example of that one just to show how that would work. So let's have a beam, let's stick a pivot over here, let's put some forces on. So if I've got a force here, let's say I've got 10 newtons, and let's make that be 2 meters away from the pivot, perpendicular distance. Let's have a 2 Newton force, and let's have that 3 meters away from the pivot. And then let's have another force here that we're going to call X, and we don't know what that is, but that's going to be a total of 5 meters away from the pivot. So if the beam is balanced, what it means is this 10 newtons acting 2 meters away from the pivot is obviously having an anti-clockwise effect. If it's balanced, this 2 newtons here having a clockwise effect, and this force unknown here having a clockwise effect, together, that clockwise effect plus this clockwise effect must be equal to that anti-clockwise effect. So they love questions like this, and there's a standard method of working these out. So your first line is always this. This symbol you'll see in maths, I think it's a capital sigma, that says sum of the anti-clockwise moments equals sum of the clockwise moments. So that straight away says that anything that's turning anti-clockwise is being equal by all the things that are turning it clockwise. Then we write out what we've got. So anti-clockwise, we've got, use the brackets, we've got one 10 Newton force, that is 2 meters away. That's all we've got acting anti-clockwise. There isn't anything else here that's acting to turn this anti-clockwise. Incidentally, you could have a force pushing up on this side. That would be having an anti-clockwise effect. So if it was there, you would add it onto this side of the equation. Equal to. So clockwise, we've got two things. So use the brackets to separate them. So we've got a 2 Newton force. That is 3 meters away from the pivot. So this brackets section here shows we're dealing with the turning effect of this force and that distance. And then we've also got, so added to that, we've got another force. We don't know the value of this force, so we call that X, but we do know that that is 5 meters away from the pivot. So this layout is really good because it means you're less likely to make mistakes in that each set of brackets represents the turning effect because of one thing. So the 10 newtons and the 2 meters, that's the turning effect anti-clockwise because of this. The 2 newtons and the 3 meters is the turning effect clockwise because of this force and this distance. And then the unknown force, which is 5 meters away from the pivot, is also having a clockwise effect. So that little set of brackets there shows the turning effect of this force at this distance. And obviously the thing we're trying to work out here is this one. So there's lots of things we can work out in this first to simplify it. So 10 times 2 is obviously 20 Newton meters. 2 times 3 is obviously 6 Newton meters. Plus we've still got here X times 5. Strictly speaking, you don't need the brackets here, but keep them there because it's separate. So we've got 20 equals 6 plus something. So we can get the summing on its own by subtracting 6 from both sides. So 20 Newton meters minus the 6 Newton meters is going to equal X times 5. Again, keep the brackets there to show that we're still talking about that turning effect. Just makes it a bit easier to follow the thing, the calculation. 20 minus 6 is obviously 14 Newton meters, equals the force X times the 5 meters that it is away. So now I can divide both sides by 5, so 14 Newton meters divided by the 5 meters will equal X, which gives us 2.8 newtons. So what that means is, in order for this to be balanced, this force X must therefore be equal to 2.8 newtons if it's being pushed or applied 5 meters away, perpendicular distance from the pivot. And then that shows that this force at that distance plus this force at that distance, clockwise effect of the first one, clockwise effect of the second one, those together equal and cancel out the anti-clockwise effect of the one on the left. So anything they give you in moments is just further examples or application of this. So there are lots of examples and questions also attached to the task which you can have a look at and have a go through. The only other thing we need to mention at this point is a tiny section on gears. So gears are used to change motion, and they can change two things in the motion. They can change the direction of the motion, of the rotatory motion, but they can also change the speed and the force of that. However, for the GCSE, you only need to worry about the effect of a change in direction. So let me draw out some gears and let's use this as a quick example. So gears are usually circular discs and they have teeth around the edge. And what that means is that the as the teeth rotate, the teeth rotate round with it. So obviously the speed of rotation will change out what else is happening there. If you connect one gear to another, then what happens is as those teeth intermesh, and you have to excuse the slightly appalling drawing here because obviously the sizing of the teeth and then the spacing of the teeth is really important, one gear turning is going to then turn the next gear. So if the first gear here is turning in a clockwise direction, then that's going to cause the gear it's connected to turn in the opposite direction. And then you can use various combinations of these to change the turning effect from one point of the machine to another. So all sorts of examples in car engines, etc. Speed-wise, you don't really have to worry too much, but the fact is, if you've got a smaller gear turning a larger gear, the larger gear is going to turn more slowly than the smaller gear. So if I were to change these to show that, then what you've got here is, here's the smaller gear turning fairly quickly, clockwise. That connected to the larger gear turns that gear anti-clockwise, but that gear is going to turn more slowly. And then you can combine those in various ways. So I can move the next gear up against this one. And as you can see, that one is now turning clockwise. So the easy thing to do here is you just draw yourself little arrows over the gears to show yourself what's going on. If they're trying to be, also notice, that the smaller gear here is now turning more quickly than the gear before it, because that was a larger gear. And the other thing to bear in mind is if you want to be a little bit sneaky, you can have different gears sat on the same axis or bar. So I can move this one in, and so this small gear attached to the same axis as this one will rotate at the same speed as the large gear. So the smaller gear rotates on the same axis as the large gear, rotates with it, so the smaller gear is also turning, in this case, anti-clockwise. So this one's turning anti-clockwise. And then you could have another gear sat on a different axis coming off this wheel, which would then also be turning clockwise. And so you can use these to string out a series of combination of gears to drive different mechanisms at different speeds, all off the same initial rotating motor. So all you will get asked is, if this one is spinning this way, then what is cog D over here? What direction is that spinning in? They might ask you to compare speed. So if this is going at a certain speed, that one's going to be slower. That one's then going to be faster than that again, but you won't have to do any calculations to work out speeds, so you just have to use a bit of a common sense approach for that.